In this video, we're going to talk about exactly how you perform implicit differentiation. Now, to understand how this works, you need to understand the chain rule. So if you aren't comfortable with the chain rule and how the chain rule works, go back a few videos from here in the playlist and watch the chain rule example problem videos. Watch the video where we go through the textbook and talk about the chain rule. Watch all the chain rule videos, get comfortable with it, and then come back here, and then you'll be able to understand this. But again, you really have to understand the chain rule to understand how implicit differentiation works. So the idea is we've got an implicitly defined function. This is an equation where y is implicitly defined. So if you come, this equation, if you come here, this is a circle, right? This is x squared plus y squared is equal to 25. But you can see y is the dependent variable and x is the independent variable. So that's why we don't say x is implicitly defined here. The assumption is that y is implicitly defined. Now you could do it the other way and say that x is a function of y and y is the independent variable. That's fine, but I'm just noting that for these problems, that's the way we're looking at it. That y is the dependent variable. Y is implicitly defined in these equations that we're going to be working with. And so the idea is we want to find dy dx. We want to find y prime. But this is different because, again, y is implicitly defined. Now we could solve for y here, y strictly as a function of x. We would get y is equal to plus or minus the square root of 25 minus x squared. We could take the derivative of both of those functions. But that's a lot messier and more difficult. But then furthermore, you can have y is equal to plus or minus the square root of 25 minus x squared. But that's relatively simple compared to other implicitly defined functions or equations. In fact, there's some where the implicit equation is not too much more complicated than this, and it's impossible to solve explicitly for y. So we need to understand how to do implicit differentiation to get dy dx of functions like this. Right, we want to be able to find the slope at any point on this curve, right? And so how do we do this? So we want to find dy dx y prime of y starting with this relation here. We're going to do this using the chain rule. That's the main tool we're going to use to do this. So what we do is we take the derivative of the entire equation, or in other words, take the derivative of both sides with respect to the independent variable, so with respect to x. Okay, so what do we have? If we distribute this, you have d dx x squared plus okay, so that's simple enough, right? That makes sense. And so, okay, let's come to each of these and find the derivative. The derivative with respect to x of x squared. This is just a normal derivative, right? When we distribute the d dx, if we just have an x term that's strictly a function of x, just take the derivative as like normal. So we use the power rule here. This is 2x plus. Okay. Now this is the only part you have to understand how to do right to do implicit differentiation. This is it. Whenever you have d dx of some function that has y in it. Okay. And actually, before we get to, let's come back here. Let's come back to this derivative again. If you remember from the chain rule videos, one trick that you can use to help with the chain rule is you remember that no matter what derivative you're finding, you're kind of always using the chain rule. Like here when we got this was 2x, we still kind of use the chain rule. Why? Because we said, okay, what is the derivative with respect to x of something squared? Some function of x squared. Well, it's 2 times that something, right? And then the chain rule, we say times the derivative of that something, times the derivative of that something, that function of x. Well, in this case, that's just x. So this is 1. So we don't put anything. It's just 2x. If this x and the x squared, so let's say it was sine of x squared, well, then we would say times the derivative with respect to x of sine of x, of that something, right? It would be 2 sine of x times the derivative with respect to x of sine of x. So you see how we kind of use the chain rule here. We just don't say it because we know we're just taking the derivative with respect to x of just x, which is 1. Okay, so we just kind of use the chain rule there. So when we come here, it's the same exact thing we just did here. We say, what is the derivative with respect to x of something squared? Some function of x squared. Y is a function of x, right? That's what we were talking about. We were assuming that y was the dependent variable. Y is a function of x here. Like, look at the graph here. Y is the dependent variable. Y is a function of x. That's what you have to remember. Here, x is the dependent variable. X is not a function of anything. So the chain rule, this is just 2x. Here, y is a function of x. We have the chain rule here. We've got some function of x squared. Okay? You really got to understand this. So what is the derivative with respect to x of something squared? Something meaning some function of x squared. It's 2 times that something times the derivative of that something. What is the derivative with respect to x of y? That's dy dx. That's what we're looking for. I'll just put y prime, but that's dy dx. You see? Here, when we did that, we said times the derivative with respect to x of that something. That was just x. That was dx dx. That's 1. Here, it's dy dx. Okay? Is equal to, what is the derivative with respect to x of 25? That's just a constant. 0. Okay, so once you get to this step, all we do now is solve for y prime and we're done. So 2y prime is equal to minus 2x if we subtract 2 from both sides. So y prime is equal to minus x over y. And that is y prime, which is interesting, right? The derivative is a function of the function itself. But this is easy though. What it's saying is you come to any point on this circle and you have the x and the y coordinate, right? We'll just divide the x coordinate by the y coordinate and multiply it times minus 1. That's the slope, right? We know we have a vertical tangent here. Well, if you plug in y is equal to 0, that's you can't. The derivative doesn't exist, but the limit as y approaches 0, it is going towards infinity. Plus or minus infinity, depending on, this would be plus infinity, this would be minus infinity. Okay? So this is a lot simpler than if we solved for y, got y is equal to plus or minus the square root of 25 minus x squared and took the derivative of each one of those functions. And again, that would, for an implicitly defined function, that would be relatively simple compared to some other functions. So implicit differentiation is really valuable, and we need it. Okay, here's another curve. This is called the folium of Descartes. Or Descartes. Maybe that's Descartes. All right, let's find y prime. We want to know at any point on this curve, what is y prime? This is much more difficult to solve for y explicitly as a function of x. A computer, by hand, it would take you forever. A computer algebra system can do it, and you get like these 3 big functions, these 3 separate big functions. Like it's like they define them kind of piecewise, because this isn't a function, right? This as it is isn't a function, but you can solve for pieces. So, but we're going to see here, we're going to find y prime quickly and easily with implicit differentiation. Okay, so let's take the derivative with respect to x of the entire equation. Okay, yeah, we're assuming that y is the dependent variable, right? And so you need to know which one's the dependent variable so you can, because it makes a difference, right? We couldn't, if y is the dependent variable here, we can't take d dy. because x is not a function of y. I'm not saying you couldn't take you could absolutely solve for x instead of y and get x as a function of y. But then you would be saying that, well, then x is the dependent variable. But you can't like mix the two. You can't mix the two. You're going to have to say beforehand which one's the dependent variable, which one's the independent variable, and then go from there. We're saying that y is the dependent variable. Okay, so if we distribute that d dx, okay, d dx of x cubed, that's just 3x squared. Okay, d dx of y cubed, this is exactly what we did in the previous problem. What is the derivative with respect to x of some function of x, of something cubed? It's 3 times that something squared times the derivative of that something. Okay, what do we do here? Well, we have 6x times y. We have 6x times some function of x. That's two functions of x multiplied by each other. We can use the product rule here. The product rule with this being your f of x and this being your g of x, right? So what is the derivative of the first? What is the derivative with respect to x of 6x? 6 times the second plus the derivative of the second, y prime, times the first, right? The derivative of y of x with respect to x is just y prime. Well, there we go. Now we just need to solve for y prime. All right, so let's subtract. Let's bring the y prime terms to one side and all the other terms to the other side. So if we subtract both sides by 6x y prime, we get okay, and then subtract 3x squared from both sides. Okay, now let's factor out a y prime here. Okay, so y prime is equal to dividing both sides by 3y squared minus 6x. Okay, but we can factor out a 3 here, and we get, and then we can factor out a 3 here. So we're left with and that's y prime. That was quick and easy. This is a simple function, way simpler than if we tried to solve for y explicitly as a function of x. Immensely simpler. And again, this is not even that complicated. You make an implicit equation a little more complicated than this. Some are impossible to solve for y explicitly. So, but again, what does this mean? At any point on this curve, you have a coordinate, an xy coordinate. Just plug in your xy coordinates here. Okay. Here is this sine of x plus y is equal to y squared cosine of x. That's this here. What is y prime? Okay, so we've got sine of x plus y. Okay, so take the derivative of both sides, or take the derivative of the entire equation. So we've got okay. So this is all the chain rule. If you're comfortable with the chain rule, and you just see how, look, you have y as a function of x and x is the independent variable, then there shouldn't be a problem. This is just the chain rule. Okay? So what is the derivative with respect to x? Let's do the chain rule. Start from the outside. What is the most general function here? We have the derivative with respect to x of the sine of something. What is that? That's equal to cosine of that something times the derivative of that something. If that was just x, well, that dx is 1. This is not just x. So we say, what is the derivative with respect to x of that something, of x plus y? Okay? The derivative with respect to x of just x is 1, plus the derivative with respect to x of y. That's dy dx. You could put dy dx. That's fine, but I'm just putting y prime. Right? All of this times that. Okay? Okay, what do we have here? We have a function of x times another function of x. Product rule. Okay, derivative of the first. What is the derivative with respect to x of y squared? Now we have to use the chain rule. So that it's just more steps here, but it's all the same process over and over again. Right? We're taking the derivative of the first. So what is the derivative with respect to x of y squared? Okay, chain rule. We have something squared. What is the derivative with respect to x of something squared? That's 2y times the derivative of that something, y prime. Okay, that's the derivative of the first times the second plus the derivative of the second. Well, what is the derivative with respect to x of cosine of x? That's minus sine of x times the first. Okay, so that's kind of, I don't know, it looks like this y squared is part of the argument of sine. Let's do y squared sine of x. There you go. That's it. Now it's just algebra. Just solve for y prime and you're done. Okay, so let's distribute everything and then bring all of the y prime terms to one side and then the other terms to the other side. So we've got y prime cosine of x plus y plus cosine of x plus y is equal to 2y y prime cosine of x minus y squared sine of x. All right, let's bring all the y prime terms to the left. Y prime cosine of x plus y minus 2y y prime cosine of x. Okay, and now on the right side we'll have minus y squared sine of x minus cosine of x plus y. So now we can factor out a y prime here. Okay, we can take out a minus sign here. Okay, so now let's divide both sides by this. So we're left with, what we could do is bring this minus sign into the denominator. So we can write the denominator as 2y cosine of x minus cosine of x plus y, and then y squared sine of x plus cosine of x plus y. And there you go. That's come to any xy coordinate here. If you want the derivative, just plug in that xy coordinate here. And so that's implicit differentiation. Next, we're going to work a bunch of problems so you can get the hang of this. We're also going to do an example where we find y double prime. And you can imagine all we would do for that is we could come back here once we get to this step, or maybe this step. Once we distribute everything like this, we would just do d dx again. And, well, okay, no, we would do what we just did here. We'd get y prime like this. Okay, so we'd have y prime. Then we'd come back here and take d dx again, do those derivatives. We would have y double prime now, right? Because like the d dx of y prime is y double prime. Solve for y double prime, and that's going to be in terms of x, y, and y prime, and then plug this y prime into that equation. So obviously that would be pretty complicated for this example. We're probably not going to work an example this complicated, but that's the idea. Okay, see everybody in the next video.